formula to convert megawatts to kilovolt-amperes is kilovolt-amperes equals megawatts divided by power factor. In this formula, kilovolt-amperes is the kilovolt-amperes value you are trying to find. Megawatts is the power in megawatts. Power factor is a dimensionless number that represents the ratio of the real power, measured in kilowatts, to the apparent power, measured in kilovolt-amperes. The power factor is a crucial element in this calculation, as it reflects the efficiency of electrical power usage. Without the power factor, an accurate conversion from megawatts to kilovolt-amperes is impossible. In the specific scenario of a 7.5 megawatt transformer with a 12.4 kilovolts primary and 4160 volts secondary, the conversion to kilovolt-amperes requires the power factor. Since the power factor isn't explicitly provided, a typical value for transformers, which is 0.9, can be assumed. Using this assumption, the calculation proceeds as follows: kilovolt-amperes equals 7.5 megawatts divided by 0.9. This calculation yields a result of 8.33 kilovolt-amperes. Therefore, the 7.5 megawatt transformer, given the assumed power factor of 0.9, has a kilovolt-amperes rated of 8.33. It's crucial to remember that this result is based on the assumption of a 0.9 power factor. In real-world scenarios, the actual power factor can vary, affecting the kilovolt-amperes rating. If the actual power factor is known, it should always be used in the calculation for a more accurate result. Understanding the relationship between megawatts and kilovolt-amperes is essential in electrical engineering. Megawatts represent the real power, which is the power actually used to perform work. Kilovolt-amperes, on the other hand, represent the apparent power, which is the total power flowing in a circuit, including both real and reactive power. The power factor is the cosine of the angle between the real power and the apparent power, indicating how effectively the electrical power is being used. A power factor of 1 indicates perfect efficiency, where all the apparent power is being used as real power. A power factor less than 1 indicates that some of the apparent power is reactive power, which does not perform useful work. Transformers are rated in kilovolt-amperes because they must be able to handle the total apparent power flowing through them. The kilovolt-amperes rating indicates the transformer's capacity to deliver both real and reactive power without overheating or experiencing other issues. When selecting a transformer for a particular application, it's crucial to consider both the real power requirements in megawatts and the expected power factor. This ensures that the transformer has sufficient capacity to handle the apparent power demand. Moreover, it's important to understand that the power factor can vary depending on the load connected to the transformer. Inductive loads, such as motors and compressors, typically have lagging power factors, while capacitive loads, such as capacitors, have leading power factors. Power factor correction techniques can be used to improve the power factor of a system, reducing the amount of reactive power and improving the overall efficiency. These techniques often involve adding capacitors to the system to compensate for the inductive loads. In addition to the power factor, other factors can also affect the kilovolt-amperes rating of a transformer, such as the ambient temperature, the altitude, and the cooling method. Transformers are designed to operate within specific temperature limits, and exceeding these limits can damage the transformer. The altitude can also affect the transformer's rating, as the air is thinner at higher altitudes, which reduces the transformer's ability to dissipate heat. Different cooling methods, such as air cooling, oil cooling, and water cooling, have different capabilities for removing heat from the transformer. Therefore, when selecting a transformer, it's crucial to consider all of these factors to ensure that the transformer is properly sized and can operate reliably under the expected conditions. In summary, converting megawatts to kilovolt-amperes requires understanding the power factor and its role in electrical power calculations. While a typical power factor can be assumed, using the actual power factor for a given application will provide the most accurate result. Considering all relevant factors, including power factor, ambient temperature, altitude, and cooling method, is essential for selecting the appropriate transformer for a specific application. It is also important to regularly monitor the power factor and implement power factor correction techniques if necessary to improve the overall efficiency of the electrical system. In practical applications, the power factor is often measured using power quality meters or analyzers. These devices can provide real-time measurements of the power factor, voltage, current, and other electrical parameters. By monitoring these parameters, engineers can identify potential problems such as low power factor or harmonic distortion and take corrective actions to improve the system's performance. Furthermore, it's worth noting that power factor correction can also have economic benefits. Many utility companies charge penalties for low power factors, as it increases the load on the grid and reduces the overall efficiency of the power system. By improving the power factor, companies can reduce these penalties and save money on their electricity bills. In addition to using capacitors for power factor correction, other techniques can also be employed, such as using synchronous condensers or active power factor correction devices. Synchronous condensers are synchronous motors that are operated without a mechanical load. They can generate or absorb reactive power, depending on the excitation current. Active power factor correction devices use electronic circuits to dynamically adjust the power factor in real time. These devices can provide more precise power factor correction than capacitors, but they are also more expensive. When choosing a power factor correction method, it's important to consider the specific requirements of the application, the cost of the equipment, and the potential economic benefits. In some cases, a combination of different methods may be the most effective solution. Overall, understanding the conversion between megawatts and kilovolt-amperes, along with the importance of power factor, is crucial for electrical engineers and technicians. By properly managing the power factor, engineers can ensure the efficient and reliable operation of electrical systems, reduce energy costs, and minimize environmental impact. It's also important to stay updated on the latest advancements in power factor correction technology to implement the most effective solutions for different applications. This includes understanding the capabilities and limitations of different power factor correction devices, as well as the impact of harmonic distortion on power factor measurements. Harmonic distortion can occur due to nonlinear loads, such as electronic devices and variable frequency drives. These loads can generate harmonic currents that distort the voltage waveform and affect the accuracy of power factor measurements. To accurately measure the power factor in the presence of harmonic distortion, it's necessary to use specialized power quality meters that can analyze the harmonic content of the voltage and current waveforms. These meters can provide a true power factor reading that takes into account the effects of harmonic distortion. In addition to power factor correction, it's also important to consider other aspects of power quality, such as voltage sags, voltage swells, and transient disturbances. These events can disrupt the operation of sensitive equipment and cause damage to electrical systems. Power quality monitoring equipment can be used to detect and analyze these events, allowing engineers to take corrective actions to prevent future problems. This may involve installing surge suppressors, voltage regulators, or uninterruptible power supplies. Furthermore, it's important to follow established standards and guidelines for power quality management. These standards provide recommendations for maintaining power quality within acceptable limits and ensuring the reliable operation of electrical systems. In conclusion, the conversion of megawatts to kilovolt-amperes is a fundamental concept in electrical engineering that is closely related to the power factor. Understanding the power factor and its impact on electrical system efficiency is essential for engineers and technicians. By implementing power factor correction techniques and monitoring power quality, engineers can ensure the reliable and efficient operation of electrical systems, reduce energy costs, and minimize environmental impact. In addition, continuous learning and staying updated on the latest advancements in power quality management is crucial for maintaining a competitive edge in the field of electrical engineering. Also consider the location of the transformer. The altitude can affect the transformer's ability to dissipate heat. At higher altitudes, the air is thinner, which reduces the effectiveness of air cooling. This can lead to overheating and reduced lifespan of the transformer. Therefore, When installing a transformer at a high altitude, it may be necessary to direct the transformer's kilovolt-amperes rating or use a different cooling method, such as oil cooling. Another factor to consider is the ambient temperature. Transformers are designed to operate within a specific temperature range. If the ambient temperature exceeds this range, the transformer's lifespan can be significantly reduced. Therefore, it's important to ensure that the transformer is installed in a well-ventilated area or use cooling equipment to maintain the ambient temperature within acceptable limits. Furthermore, the type of load connected to the transformer can also affect its kilovolt-amperes rating. Nonlinear loads, such as electronic devices and variable frequency drives, can generate harmonic currents that increase the transformer's losses and reduce its capacity. Therefore, when connecting nonlinear loads to a transformer, it may be necessary to oversize the transformer or use harmonic filters to mitigate the effects of harmonic currents. In addition to these factors, it's also important to consider the transformer's insulation class. Insulation class determines the maximum temperature that the transformer's windings can withstand without degrading. Higher insulation classes allow for higher operating temperatures, which can increase the transformer's capacity. However, higher insulation classes also tend to be more expensive. Therefore, it's important to select the appropriate insulation class for the specific application, taking into account the expected operating temperature and the cost constraints. Another important aspect of transformer management is regular maintenance. Regular maintenance can help to identify potential problems before they lead to failures. Maintenance activities may include inspecting the transformer for signs of damage, testing the insulation resistance, checking the oil level and quality, and tightening connections. In addition, it's important to keep the transformer clean and free from dust and debris. Dust and debris can insulate the transformer and reduce its ability to dissipate heat. Finally, it's important to have a well-defined emergency response plan in case of a transformer failure. The emergency response plan should include procedures for isolating the failed transformer, restoring power to critical loads, and replacing the failed transformer. It's also important to train personnel on the emergency response procedures. In conclusion, converting megawatts to kilovolt-amperes is a fundamental concept in electrical engineering that requires careful consideration of the power factor, ambient temperature, altitude, load type, insulation class, and maintenance practices. By properly managing these factors, engineers can ensure the reliable and efficient operation of transformers and electrical systems. Remember, while the conversion from megawatts to kilovolt-amperes might seem straightforward with the formula, practical applications demand a more nuanced understanding of the factors at play. Always consider the specific conditions and load characteristics when determining the appropriate kilovolt-amperes rating for a transformer.